Good day everyone, this is Sohaila from the University of Melbourne and it's a joint paper with Dr. Robert Crawford. A comparative study of life cycle greenhouse gas emissions of panelized prefabricated residential walling systems in Australia. I'll start the presentation with the statement of the problem that sparked the research and the literature which led to the research question. Then I'll continue with describing the research approach and discussing the results. At the end, I'll conclude the presentation by proposing areas for future research. The global warming has brought out enormous changes in the environment. Buildings are one of the main contributors in global warming, accounting for 39% of energy-related greenhouse gas emissions. Residential buildings account for 17% of these emissions. With the projected doubling of population in the next 40 years, these houses represent a significant opportunity for greenhouse gas emission reduction. In Australia, regulations like the 6-star standard for residential buildings attempt to address this issue, but the construction of buildings has been shown to contribute as much to building-related greenhouse gas emissions as their operation. Therefore, it is critical to not only decrease the operational greenhouse gas emissions of residential buildings, but also to ensure minimum greenhouse gas emissions associated with their construction. To date, in an attempt to improve the environmental performance of buildings, several strategies have been adopted. Prefabrication is one of these novel building methods. It has been demonstrated that prefabrication can improve the environmental performance of buildings through lower resource input, reduction in waste, and improved quality. However, little research exists on whether it reduces construction-related greenhouse gas emissions. When looking at the literature, systems applicable to detached houses and their benefits are rarely studied, especially in the Australian context where 73% of all Australia's residential dwellings are detached houses. Besides, almost all rely on a process analysis approach, which can exclude up to 87% of the energy requirements and its associated greenhouse gas emissions. Therefore, the aim of this study was to compare the construction-related embodied greenhouse gas emissions of detached residential housing in Australia using conventional construction and panelized prefabricated external wall systems. So, to see whether panelized prefabricated walling systems are capable of reducing the construction-related greenhouse gas emissions of detached residential housing. In order to evaluate the construction-related greenhouse gas emissions of these prefabricated houses, this study focuses on the initial embodied greenhouse gas emissions, module A1 to A5. As you can see, it includes product stage and construction process stage. For the purpose of this research, a typical detached dwelling was selected as a case study house and considered to be located in Melton, Victoria. The house has a gross floor area of 202 square meter and represents a typical Australian detached house. The house's original brick veneer construction was selected as the base case scenario, as a 70% share of the residential building stock in Australia associated with brick veneer. 3 alternative external wall systems were selected to be representative of emerging innovative timber-based panelized prefabricated walling systems suited to detached houses in Australia: cross-laminated timber, structural insulated panels, and prefabricated timber-framed panels. The design of the selected external wall systems is based on the common practices of companies designing and constructing these systems in Australia, and also to satisfy minimum regulatory requirements of a residential building in Melbourne, including a minimum external wall R value of 2.8. Finishes were selected to allow for direct comparison between scenarios. While there is a variation in external wall widths, the architectural details and other parameters of the case study house are identical across the 4 scenarios. The initial embodied greenhouse gas emissions calculated in 2 stages: product stage and construction process stage. To quantify the product stage emissions, a path exchange hybrid life cycle inventory approach was used. So, the quantities of materials for each scenario, including a wastage factor, multiplied by the respective embodied greenhouse gas emission coefficient provided by EPIC database. The coefficient represents the total direct and indirect greenhouse gas emissions associated with the extraction of raw material through to the factory gate per unit of material. When using prefabricated components, the wastage factor considered to be 0. The construction process stage greenhouse gas emissions of the case study house, excluding its external walls, quantified using environmentally extended input-output data. Because more specific data on the greenhouse gas emissions was not readily available, and also as all elements of the study house are identical for every scenario except the external walls, the quality of data used for these elements was considered to not influence the comparison of scenarios. But a detailed process analysis was used to quantify the construction process stage greenhouse gas emissions of each wall system. This approach breaks down the construction process stage into transportation, construction process, and supporting services, and facilitates a detailed comparison. To quantify the transportation greenhouse gas emissions, the emission factor per ton kilometer of each transportation mode was multiplied by the quantities of the materials or equipment being transported and its distance from the production site to the construction site. To quantify the emissions associated with diesel or electricity-powered equipment, the emission factor for these equipments multiplied by the duration of their operation. As for the supporting services, the cost of the external walls and the environmentally extended input-output data used to quantify the emissions associated with these services. The analysis of the initial embodied greenhouse gas emissions of the brick veneer scenario shows that a total of 122 ton carbon dioxide results from the construction of the house. The brick veneer external wall system was found to represent 15% of these emissions. This highlights the significance of exploring alternative walling systems to reduce housing-related emissions. It also shows that the timber-framed panel is the only option that provides a significant reduction by 7% compared to the brick veneer, while structural insulated panels increase the initial embodied greenhouse gas emissions by 6%, and the CLT increases it by 1%. The result emphasizes the importance of product stage greenhouse gas emissions, which account for around 70% of the total initial embodied stage for the fourth scenario, and the importance of selecting materials with low emission intensity. For example, because structural insulated panels have one of the highest embodied coefficients, they resulted in higher initial embodied emission in the respective walling system. Construction process stage results show all three alternatives lead to an increase compared to the brick veneer results, with the highest increase for the cross-laminated timber. This is mainly because of the necessity of heavy machinery and additional supporting services for the construction and installation process of prefabricated panels. When looking at the wall itself, it illustrates the effect of prefabrication on greenhouse gas emissions of transportation and construction equipment. However, their proportion is less than 5 and 7% respectively in the worst-case scenario. It also shows the use of prefabrication has increased the greenhouse gas emissions associated with diesel-powered construction equipment because of the necessity of mobile crane in the installation process of the prefabricated panels. This study developed a unique detailed embodied greenhouse gas emission analysis of panelized prefabricated systems compared to the conventional construction of detached houses in Australia. However, as with any research, this study suffers a series of limitations, including use of a case study building, exclusion of recurrent embodied energy, and exclusion of reuse, recycling, or incineration potential of materials at the end of the life stage, which could be targeted in future research. This study showed that the on-site benefits of prefabrication, such as faster construction, may not be the critical factor for reducing housing-related embodied greenhouse gas emissions. The product stage and selecting materials with low emission intensity may have a much greater influence, and that embodied greenhouse gas emissions shall be integrated into the decision-making process for housing to ensure net reduction is actually occurred. Thanks a lot for your attention.